apples plus how many apples gives you 7 apples? Well, you would count and you would sit there and go, all right, I need 1, 2, 3 more of them to add up to equal a total. Now, this was stuff you guys did in like 1st grade, okay? You were learning how to solve for values. You were learning to figure out, remember this, fill in the missing box? Fill in the sentence of what's missing.
Where did those go?
As you went into this, this slowly turned into that. As it slowly started morphing.
Wait, there's X and then we could have already been like they could have just had X with whatever value.
They would have confused you. Trust me. So as you get into this, we knew, guys, we knew that to get to the next step, ladies and gentlemen, come on. You knew to get to the next step, guys, come on. You knew as you started to get further along in these things, you knew to work backwards. You knew that to get the answer, to solve for the missing value, you knew that you had one answer. You knew that there was only one possible solution to make that sentence work. The only number you can add to 3 to make it equal 7 was what? 4. Is there any other number you can add to 3 to have it turn into 7? No, because you're solving for one value, and that one value is 4. When you got to this, we had to get and factor it. So what times what's -6? You add together to get -1. What do you get? What were your zeros? 3 and 2. 3 and -2. This one had 2 solutions, 2 possible solutions, because there were 2 values of x. It was a squared function. So every time as you guys have been going through, and you saw that last week as we got into the higher degree polynomials. This is why all of this works, and it is because what's called the fundamental theorem of algebra. Is it fundamental? I think so. It's basically this: for every x, there exists a 0. How do they write that? I think it's f of, there's a 0. So basically, for every degree you have, you've got an answer. The basic idea is when you solve for x, you can. There's always a missing, if there's a missing value, whatever the degree is, it tells you how many missing values there are. That's basically what all this boils down to. It's why every time you guys have been able to solve for x, you got solutions. You always had an answer because there was an answer. Okay? And that's how this stuff goes. As we get into this more, we start to go into higher degree polynomials. And I'm really sorry about the board being all messy. When I look at this one, think about now all the bits and pieces we know. What's the degree of this function? 4. What are the tails doing? Tails are up. We know that it's got a 4th degree, which means how many possible zeros can it have? 4. How many terms are in the sequence? 5. How many total changes of directions could it have in the graph? 3. Remember the rules here. Your nth degree is possible zeros. n plus 1 is number of terms. n minus 1 is possible changes of direction. Let's call it changes in graph. If you think about it, what's a squared term? When we are squared, we are up like a cup or down like a frown. Where's your change of direction? It's at the vertex, wasn't it? Same basic principle. So you had that one change in direction because it was 1 less than that. So as you went into this then, we also started to realize that we knew the tails. In this case here, our tails were positive, degree, and it was even. So our tails were up, up. You also in this problem know exactly one extra point that you could plot. What is it? Where is that? Good. So you also have a y-intercept in this case because the y-intercept occurs when x is equal to 0. So the whole, remember when we did all that cover and solves earlier in the school year before it was, Siberia? So the same idea. The reason why all this stuff starts to work is because we know solutions. So as you go into this one, now from last week, we know how to start this. If I didn't tell you where to start, you would have been like, oh. So you would have to list your factors. What are your factors of 27?
1 through.
And our first term is 1, so it's just all over 1. Okay. All right. Does it matter what value you start looking for? Nope. Pull your coefficients. Make sure they are in descending order. And you just start going. As you do these things, you should start to recognize when a number isn't going to work to cut your losses. All right. So as I start going through here, 1, 1, 5, 5, -1, and I can tell right now it's not going to get me any further. Okay, because now I'll be at, what does that be, -1 will be at -37. That's not going to get me to 27. So I just erase, and I try -1. All right. Yes, sir. Huh? Possible, yeah. And the nth degree was possible changes in direction. So if it's a fourth degree, it means it could change direction up to 3 times. There are some instances where you have a fourth degree polynomial that changes just once, because you have imaginary solutions as well. Correct. Yep. Let's say you have imaginary solutions at plus or minus 2i, and then you just don't know where it's changing. It doesn't change it. You could have, what's the problem? If you do, go to your calculator real quick. I think, let me see. I don't have it out here. Go to your calculator, pass the I equals. I'll show you what, then I'll do that. Don't drop it.
Definitely a home run.
Bat flip, but I didn't see it. That was the Bodie walk-off a couple years ago, bottom of the ninth. What game?
It's not.
That was the Nationals game?
I know, it's the third year.
No, it was regular season. It was right before the school.
I got golden girl yesterday.
Yeah.
I stopped watching a lot of baseball.
This was this was 2 summers ago.
I remember it happening, but I wasn't watching.
It's overrated.
Just like I don't think I watched Game 7. I'm just like, I don't think I watched it. I'll find out tomorrow.
Yeah.
You knew about the
All right, so now
Nope.
let me clear mine out real fast, and I'll show you a function to throw in there. So, do you agree that if I wanted an imaginary solution, like it would be x squared plus 4? You okay with that? So let's do this. Do parentheses, x squared plus 4, close your parenthesis, and then we'll put in x minus 1, parenthesis, x plus 3, parenthesis. That gives us a 4th degree. You okay with that? You okay? That's 4th degree?
Yes.
So if I hit graph, how do you know it's 4th degree? Squared, there's 4 x's, there's a squared and 2 other x's. So here my window's a little messy because I was just trying to think of a problem here. So let me change my window to a plus or minus 30. And if I look at this, I think this will show up now. See how it just looks like a regular B?
Yeah.
Even though it's a 4th degree polynomial, it only has 1 change in direction. The reason being is that there's imaginary solutions to it. So that's why it starts to look like that as you're going through. It's graphing anything that has imaginary is something that we really don't do. So anytime I ask you to plot your zeros and do your tails, you're going to have real solutions. So that's kind of what we can do. I'll have your factor all day long. You can give me imaginary answers, but I'm not going to be able to actually graph them. Is that kind of what you were asking about?
Yeah.
All right. So you said -1 worked? Yeah. Okay. So 1, -1, 3, -3, -9, 9, 27. Oops, sorry, -27, 27, and then 0. Now, at this point, you'll notice you have 4 terms. Look at your coefficients. 1, 3, -9, -27. What do the 9 and the 27 have in common?
9.
The 9, right? So when you start to see this, we know this is a 0. My term is x plus 1. Whenever I start to recognize this, I know that I have x cubed plus 3x squared minus 9x minus 27. If I try to group it here, it's quicker. Okay? Take out my x squared, x plus 3. Take out my -9, I have an x plus 3. Okay? So now we have x squared minus 9 as a term, and an x plus 3 as a term, which gives us zeros at -1, plus or minus 3, and -3. So when I list this, what do I write?
Would it be -1, 3, and -3 with a multiplicity of 2?
Very good. -1, 3, -3 with multiplicity of 2. Okay? So again, you could have continued to use synthetic the whole way through, would have been just fine. But at the minute you notice that you have anything remotely factorable, when you have 4 terms, look at the numbers, try and group it. Just a little bit quicker. Okay, just a little bit quicker. Alright?
If the multiplicity, you get 2 of them when you factor it out.
Yep, now this is definitely a problem that I would ask you to graph. This would be definitely a problem that I'd ask you to graph because we have the zeros. We knew that we have a y-intercept down here at -27. We had zeros at -1, -3, and +3. Our tails were up, so that means as it's working its way down towards the -3, it'll bounce down to here. We go. All right. Yes, ma'am. There's 2 of them at -3. The reason there's 2 of them because we found one of them here at -3. This was a plus minus 3.
Okay, so the plus minus.
No, just because there's 2 -3s.
Oh, okay.
Okay, remember this means there's a 3 and a -3. That's what that means. Okay. Yes, sir.
thought it only bounced to multiplicity.
It is. But there's 2 of them. You're thinking 3. Okay. All right. And if it's an odd multiplicity, it just goes through.
Oh.
What? Yeah, that's right. That's what I said. I saw it because I knew what it was. Yeah. Okay. All right. What do you do now? What's the trick there?
You do what goes in the next.
Yeah. Remember, when you have one like this, you've got 3 terms that goes, 4th degree squared constant. Try and factor it like you would any other normal trinomial. What times what's -12? You gotta get +1. And then this is -3. From there, you can get your zeros. Your zeros means you set it equal to 0 and you get plus or minus 2i and plus or minus √3. Subtract 4, take the square root. Subtract 3, add 3, take the square root. 4 possible zeros, those are your 4 zeros. Only 2 of them are real. No big deal. Okay, no big deal. Alright. Yes, sir.
Which letters on the graphical
It could change somewhere else in the middle. It just won't be at the on the axis. Yeah. And that's why I don't ask you guys to ever graph it. What times what's -12? You have 1. So here, like I said, you haven't did this one. That's easy. Let's do this one. let's get all of our zeros. Let's get all of our zeros, and if they're real, we'll see if we can plot it. Yes, sir.
No, we have a 0 at 0 already.
We do. We already have a 0 at 0. Everybody see that?
Yes.
Yes. And that's the idea here. Because you don't want to use synthetic right off the bat, because there's a 0, there's no constant, so it wouldn't help you. So we know that there has to be a 0 on the out, or at GCF. Okay. So I know that I have a term of x. So I start listing it. I already have my term. I have to worry about my tails now. Plus or minus 1, 2, 4, 8.
Getting up back to group it.
No, if you look at it, you don't have anything. See how there's nothing in common with the 12 and the 8 to get you to 1 and 6? Because if you take out a 4, you're going to get 2x. I'm sorry, you take out a 4, you get 3x plus 2. That does not match x plus 6. So in this case now, then you would start using synthetic because you took out the 1 degree at the x here being a 0. You just start over. So 1, 6, 12, 8. Just go through the motions. 1, 1, 7, 7, not going to work. Bless you. -1, 5, -5, -7, not going to work. Try it 2. 2, 12, 12, too big.
Can we cut out anything positive because we can't.
That's what I just found out last night.
That's a good pickup. Very good pickup. When you start to see that all of your numbers, in this case, see how they're all positive, your coefficients are, and they go from 1, 6, 12, 8, so you have to have a negative value to make it work. So you don't have to try the positives. So you have 4, what is that then? -8, 4, 12.
Do it again.
So satisfying.
Do it again?
Yeah.
Try -2 again? Or do you want to just use quadratic? Try -2, okay. 1, -2, 2, -4.
I like multiplicity.
Now, we haven't done this yet. We went from 3rd degree squared. What's this now? That's 1x plus 2, isn't it? Oops.
So we don't even need to put it in.
No, because you're at x plus 2. You're linear now. You're at x plus 2, because if you keep going down a degree, that's your last term. So this case has multiplicity 3 times at -2.
Wow.
So your answers here are 0 and 2 with multiplicity. So your answers are 0, -2 with multiplicity of 3. And now graphically, that just goes through -2. Okay, it just goes through -2. There's probably some weird jog in the middle somewhere, but for us, I'll probably only have you graph. I won't. The graphs that I have you guys doing usually are even bouncing multiplicities because it's a little bit cleaner to make them go. Then just go graph. Yes, sir.
I answered my own.
That was a great conversation between your brain and you staring at your fingers. So that was really good. Yeah, this one was up. This would be up, and then you go through 0 and -2. So I'm guessing it probably, you had the 0 here. It probably just did this somehow. It's probably all it looked like. There might be a little bounce, and there might be something under. I don't think there'd be anything else than that. Because you take out the x. Okay. Oops.
Wait,
What time is it? All right, we got time. All right, do this one real fast. Factor, give me all my zeros. Give me all my zeros. All zeros.
all
All of
All of them. I I want all of them. Give me all of your zeros. I am very greedy, but I'm asking for nothing.
Was not that funny.
I thought that was good.
I just
I like
I thought that was good. I'm asking for nothing.
It wasn't bad.
Alright, so this is started there. Third degree. Just try one till it works. This is expert. You can't roll out the negative square. That doesn't get a negative number.
It's only don't be zero.
We're going to need a zero.
I know.
Just one more. Does it? Got me excited for no reason.
Have to work again.
No, it doesn't work.
Wait, how does that work?
It doesn't work.
How does that work?
Yes, it does. The first try. It does. Because if you one time negative,
No, it's 1 times 7. No,
Yeah.
what are you doing with that language? Oh, that's how I can make a point. Way smaller. Oh, I just didn't use
The ruler piece, right? So you have 1, 2, 3, 6.
Whoa.
No, I was. You spoiled it.
Wait,
No.
hold on, wait, no.
No, I'm saying plus or minus for impossible.
Oh,
Spoiled it.
Wait, let's try 2.
1, -2, 0.
No, it doesn't work.
Did you guys put a 0 in for x cubed?
Yes.
No.
Oh.
Yes, I did.
Good for you. Not like these other losers.
Hey.
I knew it. I felt bad about it.
5th degree polynomial has to have 6 terms that are not 6, so you have to have a placeholder.
Luckily, it doesn't matter.
Yay!
Do it again. Wow.
So we have a 0 at 1.
Jason.
No.
Wait,
Do it again.
JC says do it again. She's all excited about it.
Wait.
We're checking for multiplicity by doing it again. 1, 1, 0, 0, -1, -1, 6, 6, 0.
Oh, we can do it again.
So I have another 0 at -1, which means right away, I'm sorry, positive 1, excuse me. So I have 2 terms right now at x minus 1, so there's multiplicity. Bless you. 3rd time's the charm, maybe?
No.
No.
Well, you can always try. You can probably tell it's not going to work. Womp, womp, womp. So try -1.
Does that work?
So then I switch over to 2.
Wait, you can whatever.
Yeah. You gotta keep going.
Except for you. JC, you were literally like a light. It doesn't work. But -2 does work. Wait, -6 will probably get 6 will work.
I just guessed that. I didn't actually know that.
-6 will work.
So now I'm at a quadratic.
Wait, no, how do
I didn't give it a
One of the things you can do, whenever you get to the quadratic, just write it and see if it's factorable. So you have x squared minus 2x plus 3. What times what's positive 3 to add to get a negative 2?
Negative 3, 1.
If it was negative 3 and 1, then you'd get negative 4 in the middle. This is where you're going to have imaginary solutions again. You have to use quadratic. It's not factorable. So you have to go to quadratic. Opposite of b plus or minus square root b squared minus 4 times a c all over 2a. 4 minus 12 is negative 8. What's the square root of negative 8?
I root 2.
How about 2i root 2? Remember the I goes after. So you get 2 plus or minus 2i root 2 all over 2, which means I can simplify this.
Plus or minus I root 2.
Whoa, what happened to the one up front? 1 plus or minus 2i. 1 plus or minus I root 2. And then our other zeros were at 1 and negative 2. So negative 2 and 1 with multiplicity. 2. Okay. Yes, sir.
I didn't like it.
Yeah, that's fine. Was it factorable at that point? Yeah, that works. Every one of these depends on what number you pick out first, how things are going to work. Because remember, if you do like a factor tree, if I want to find the factors of 12, some of you guys would say 3 and 4, some of you guys would say 2 and 6. You're going to get there, you're just taking out factors in different terms, or different times, excuse me. Okay. Speaking of terms, what if I give you zeros? What if you have zeros at 3, 4, and 2i, and I want you to write the polynomial? Actually, instead of 3, let's do 0. We'll do 0, 4, and 2i. Let's say I want you to write the polynomial with a coefficient, leading term coefficient of 1. I'll make this easier on you. I want a leading term coefficient of 1 that has those zeros of 4, 0, and 2i. And if I have zeros at 4, 0, and 2i, first of all, what are your terms? What's your term that generates a 0 at 0? X. What's the term that generates the 0 at 4? X minus 4. What about 2i?
X
squared plus 4. Remember, I did this on purpose. I's always come in pairs, don't they? They always come in pairs of plus minus. I only left you one of them. I want to see if you caught that. The only way to be able to generate an I value is if you took a square root over an equal sign. If you take a square root over an equal sign, you will always generate plus minus. So in this case here, if there's a 2i, there has to be a negative 2i. So the way what generated that would have been x squared plus 4. Okay? So now it's a matter of multiplying out. This gives me x squared minus 4x. That's x squared plus 4. FOIL it, you get x to the 4th minus 4x cubed minus 16x. I'm sorry, minus 4x. Right, sorry, I got ahead of myself. Plus 4x squared minus 16x. There's your function. There's your function that has those zeros. Makes sense because there's 4 zeros, which means what's the degree it have to wind up being? 4. Okay? Even though that there's only 3 of them listed, you just have to remember that i's come in pairs. Unless you got poke your eye out.
Is this going to be on the test?
I don't know. Why wouldn't it be? It's pretty easy, isn't it?
Oh. Yeah.
Now, here's the difference here. In this case here, I told you your leading term coefficient was 1. What if it's not? It doesn't suck. It's actually pretty easy. Let's say you have this.
You do it the same and then just put it out there?
Sorry. 2 comma, 2 0, negative 3 0, 1 0, 2. Those are 3 zeros, right?
Gosh.
You guys okay with that? There's 3 zeros there?
No.
I'm not okay.
There are 3 zeros. Everybody see that?
Yeah.
And there's an extra point, right?
Yeah.
So isn't that the same idea as saying y equals when we did intercept form, the quadratics, it was x minus p, x minus q. Here you just have higher degree, so that's x minus 2, x plus 3, x minus 1. What's your x and y value? Oh, that doesn't work with a 2. Sorry. This can't be a 2. This has to be a 3. No, it can't be a 3. Yes, it can't be a 3. I just had an argument with myself.
Okay.
It was like talking to your finger.
Yeah.
Wait.
I just made up numbers.
What is the 3?
Are those x and y's? Remember when you did intercept form, you had to solve for a? It's the same idea, just added a 0.
That's all we have to do.
Yeah.
What?
Just kidding.
We can just ignore the intercept altogether.
Why are we?
And then you just.
What is the 3?
Oh.
Oh, no, not the ordered pairs. Oh,
That makes sense.
If those are your zeros, what are your terms? If 2 is a 0, my term is x minus 2. Negative 3 is a 0, what's my term? X plus 3. And so on. What's 3 minus 2?
1.
1. What's 3 plus 3?
6.
What's 3 minus 2? 1. What's 1 times 6?
6.
What's 6 times 2? 12. So 5 equals 12a. What's a? 5 twelfths.
Wow.
That's the idea that we'll get towards. It's right, and that's how you'll be able to get your first term. You still, I mean, the numbers here I just made up off the top of my head, so they weren't clean. You'll get cleaner numbers. You just need to figure out what links your coefficients. Yes, ma'am.
so in the
Okay.
the 35 is separate from the 40.
Yeah, that point is on that curve.
So would you state that if it was in the text? Like, would you be like, okay, these are your
We're going to do more of that stuff tomorrow. I'll show you how it's going to work. It was just an offshoot of what happens when you don't have it, when your first term is not 1. This is all you would do.
That's just your first time.
No, that's A. Your first, you have to FOIL all of it out. So you have to multiply 5 halves into here and distribute everything through. It gets really messy. It gets messy. Yeah, it gets, that first term, like I said, I just made up a number and it worked kind of crappy with it. The numbers that we do with these, a lot of times they can be like 2 or negative for A value. The A values become a lot easier to work. Okay, so it's not, this is just so showing you that we've done this problem, I just added this 0. That's all I'm showing you. So it's not easy. Yes, sir. You have a question?
Oh no, I was trying to.
Good, didn't want to help. If I'm not mistaken, I posted, yes, we did this. The other one that we're going to look at tomorrow is we'll do ones where it has, which one was it? We'll do one that looks like this. We have to work a little bit with the, if there's a 1 plus I, what else should there have to be? 1 minus I. This gets a little messier. We will go through this one tomorrow. This is another, remember how we did that U substitution about a week or so ago? This is a prime case of where that comes in handy. Okay. We'll talk about that tomorrow. I posted on the calendar the problems already. I want to say it was, I forgot. I don't know. I put a couple of, there's a few table style word problems on there. To have you guys try a couple on the calculator. It shouldn't be that difficult. Let me pull up the problems here real quick. Yeah.
I don't have any.
Oh.
Well, do you just have those lying around? Pretty much. It's like everybody. You're supposed to see nothing.
I have those set in there for you.
That's pretty good.
So, those calculator ones are just basically throw them, they don't look any different than when you did the funky quadratic ones. where you were trying to use the table to figure out how long it took for something to elapse, something along those lines. Really easy. That's the only thing that we'll be using calculators for, is just polynomial stuff that are word problem like, really, really simple. Everything else is pretty much on the calculator. We'll talk about that last little bit tomorrow and go over any other things I can tell you. Yeah, I'll probably do calculator 9. It's be really easy. When you see how
April 24th.
Oh wow. I'm older than you.